In this lecture, we'll talk about the properties and use cases of hash algorithms. Though all cryptographic hash functions have different mathematical foundations, they do have the same properties. Let's consider a cryptographic hash function and see what are its properties. The first property is called determinism. This means that the output of a hash function doesn't change between executions if it runs on the same input. It doesn't matter when or on what machine you calculate the hash. It will be the same if you use the same algorithm and input. In these examples, I've calculated the hash of Word Linux in two different ways, using the SHA-512 sum command and using the OpenSSL command. It's the same hash. If I calculate the hash using an online tool, we get the same result. Another important property of hash functions is that two different inputs always have different hashes. Or we can say that if two inputs, like two files, have the same hash, they must be equal. If a single bit changes across inputs, it will produce an entirely different hash. Let's calculate the hash of the word computer using SHA-256. Computer, and the algorithm is SHA-256. This is the hash. Now, let's calculate the hash of the word computer1 using the same algorithm. We notice that two different words have two different hashes. Each input has its own unique hash. Keep this in mind. Now, theoretically speaking, it's possible to have collisions, and that means different inputs with the same hash. But with a good cryptographic hash function, there isn't a known way of finding a collision with all the computing resources in the world. We'll discuss hash collisions in a dedicated lecture later in the course. A hash function is one way, meaning that it's computationally infeasible to determine the original message from its hash value. Hashes work based on an irreversible mathematical transformation. In other words, given a hash, it would be impossible or extremely difficult to determine the deterministic steps taken to reproduce the input of that hash. Look at this hash. There is no way, no matter how much computational power you possess, to find the file or the text that has produced this hash. Hash functions always produce a fixed length output regardless of size of the input. For example, SHA-256 always produces a hash of 256 bits and SHA-512 a hash of 512 bits. In fact, the number after the SHA word means the length of the output hash. Let's see some examples. I'll calculate the hash of two characters A and B using SHA-256. This is the hash, which has a length of 256 bits or 64 hexadecimal characters. Now I'll calculate the hash of a phrase. And the output hash has the same length, 64 symbols in base 16. Let's see now the hash of a file. I'm not interested in how big the file is. Its hash will have a length of 256 bits or 64 hexadecimal characters. Sorry, the command is SHA-256 sum. Okay, permission denied. Okay, let's choose another file. etc password. Or etc group. Or /bin ls. And so on. We see the hash is the same length. If I had a file of 1 gigabyte, its hash would be of the same length. Another property of hash algorithms is the avalanche effect. Changing one bit in the input should create an avalanche effect, and its result is an entirely different hash. Let's see an example. Let's take a bigger file. For example, a dictionary file that comes with Kali Linux. Let's see how many characters and words are in that file. USR share, dict, and American English. There are almost 1 million characters. Let's calculate the hash of that file. This is the hash, and I'll change a single character. I'm opening the file using Vim, and at the end of the file, I'll add a white space. Okay, and I'm saving the file. Okay, I must be root in order to be able to edit the file. No problem, it's very easy. So at the end, I'm adding a white space, and I'm saving the file. Let's see X hash. And we notice that X hash is entirely different. It's in fact a new hash. This is the avalanche effect. These 5 properties we've just discussed are the most important ones of any hash function. A good cryptographic hash function must also provide compression, efficiency, and collision and preimage resistance. Compression means that the length of the output should be small enough. Efficiency means that the output hash should be computed easily enough in terms of time and hardware resources. And collision and preimage resistance means to be secure enough. I'll go deeper into these 2 properties in a dedicated lecture where we'll talk about the attacks on hash algorithms.